I'm Miss Hall, and this is Lesson 5, Solving Linear Systems, 2 Variables. This will be a review from Algebra 1. We're going to be solving systems of linear equations 3 different ways: graphing, elimination, and substitution. A system of linear equations simply means 2 or more linear equations. The first method we're going to review is by graphing. So when you're graphing 2 linear equations, the solution is the point or points of intersection. I picked these graphs in particular because they highlight 3 situations that can happen. In A, we have 2 linear equations that when graphed are parallel to each other, so there are no points of intersection. We say here that there are no solutions. These lines will never meet. In example B, those 2 equations have been graphed, and you'll see that there is one solution. And when there is one solution, we can write that solution out, which is the ordered pair at the intersection point. So that is 3, 1. As an ordered pair, that means the x value is 3, the y value is 1. And for C, we graphed both of those equations, and they were 2 lines, one on top of each other, which means that there are infinite solutions. They intersect at every single point. They line up exactly on top of each other. So to review, when you're solving a system by graphing, you look for the point or points of intersection. There are 3 cases that can happen. You could have no points, where there's no solution, 1 point, or infinite solutions where they meet at every single point. The next method we're going to review is elimination. In elimination, we want to add or subtract the equation so that we eliminate a variable. In problem A, I have positive 2x and a negative 2x. So if I add those 2 equations, I can eliminate the x's. 2x plus a negative 2x is no x's, they are gone. And I have negative 3y plus negative 4y is negative 7y. 3 plus negative 10 is negative 7. Divide both sides by negative 7, and I get that y equals 1. In a system of equations, we need both the x and y solution. We just have the y. To find the x, I pick either equation, substitute in my value of y, and solve for x. I'll choose the top equation because it has less negatives. And so I have 2x minus 3 times y, which is 1, equals 3. 2x minus 3 equals 3. 2x equals 6, because I add 3 to both sides. X equals 3. We typically write our solution to a system of equations as an ordered pair, x, y. Let's do the same thing for example B. However, there's nothing I can eliminate right away. If I added or subtracted these equations, the x's wouldn't go away and neither would the y's. So here I will multiply the top equation by 2 so that I get positive 4x and negative 4x. So I must multiply every term in that top equation by 2. I get 4x minus 6y equals 6. Bring the bottom equation over as is, negative 4x plus 6y equals 6. I'm getting kind of nervous because now I notice that the x's and the y's are going to eliminate. So let me take this slowly and I'm going to write the 0. So 4x plus negative 4x is 0 x's plus negative 6x plus 6x is negative 6y plus 6y is 0 y's equals 12. So this is an unusual case. Now I have to think to myself, are there any x or y values that would make this equation true? And the answer is no. Because if I multiply any number by 0, I get 0. And so it doesn't matter what I give x or y. Once they multiply by 0, there's 0. And 0 plus 0 will never be 12. I cannot give any values of x or y that will make this equation true. Therefore, there is no solution. Here is an example of a system of equations with no solution. Let's try example C. Is there anything I can eliminate? No. So I can multiply the top equation by 2 again. I get 4x minus 6y equals 6. And pull over the bottom equation. This is negative 4x plus 6y equals negative 6. Okay. Now I add, and everything's going to get eliminated again. I have 0x plus 0y equals, and this time I get 0. Okay, so this is a little different because I can think of x and y values that are going to make this equation true. In fact, any x or y value is going to make this equation true because no matter what x is, when I multiply it by 0, I get 0. And no matter what y is, when I multiply it by 0, I get 0. So this is an example of infinite solutions. So just like in the graphs above, we saw an example of no solution, one solution, infinite. We're seeing those examples now done by elimination. Final method, solving by substitution. In this method, we're going to substitute or replace one variable with an equivalent expression. We have that a equals 1/2 b minus 6. And so we're going to substitute in that expression into the a up here, 1/2 b minus 6. And what happens then is this first equation has only one variable. And I can solve an equation with one variable. So can you. Okay, so that's the big part of substitution. Isolating a variable, a was already by itself, and then replacing this variable a in the other equation with its equivalent expression. I always put it in parentheses. There might be a case where like the parentheses end up not mattering because if it was just, say for example, a plus 3b equals 12, then you could just put that expression up as the first two terms. But it's not, so I replace it within parentheses. Now I will simplify, distribute the 2, I get b minus 12 plus 3b equals 12. Negative 12 plus 4b equals 12. I combine like terms. Move that negative 12 by adding 12 to both sides. 4b equals 24. b equals 6. System of equations, I need both variables. I'm going to choose to replace b in the second equation because then a is already by itself. A equals 1/2 b, which is 6, minus 6. A equals 3 minus 6. A equals negative 3. So we could leave it as a equals negative 3 and b equals 6. If we were going to put it as an ordered pair, it's a little unusual. That's not x, y. But we could put it in alphabetical order, negative 3, 6. I would just label it at the top because it's not x and y. Okay, but you don't need to write that ordered pair. That's just extra. But you do need to find both variables, a and b.